On May 6, 1937, the German airship Hindenburg was making what should have been a routine landing in New Jersey, as families waited below to welcome passengers back home. However, within moments, the airship went up in flames. 32 seconds, 36 killed. The entire world left in shock. But how could such a disaster have taken place? Where did the design fail? How did this disaster affect the future of airships? The Hindenburg, officially known as LZ-129, was a massive passenger airship designed for transatlantic travel, with a size comparable to that of the Titanic. Built with a rigid metal frame and outer fabric layer, it used multiple hydrogen-filled gas cells and powerful engines to stay airborne and travel long distances. Its primary purpose was to transport passengers, mail, and cargo in a way that was more comfortable and luxurious than traditional ships. On the 3rd of May, 1937, the Hindenburg departed from Frankfurt, Germany, on a transatlantic flight to the United States. After several days of travel, it approached its destination at Lakehurst, New Jersey. However, rain and thunderstorms delayed its landing. Later that evening, as the airship began making its descent and dropping landing lines, a small flame was spotted at the rear of the airship. The fire spread rapidly as the hydrogen was ignited, and in just 32 seconds, the airship was destroyed. Although there are many controversial theories about how this disaster occurred, research shows that it was mainly caused by hydrogen leakage and static electricity. During landing, hydrogen escaped from gas cells, while static electricity built up due to the stormy conditions. When the landing ropes connected to the ground, the built-up static charge was discharged, creating a spark that ignited the hydrogen. This failure occurred due to a design flaw and material choice failure. The airship's use of hydrogen, a highly flammable gas, made the airship extremely vulnerable to ignition. Additionally, static electricity buildup was not fully accounted for in the airship's design. Although some theories suggest that the outer paint was highly flammable, research shows that it burned too slowly to play a major role in the disaster. When comparing helium and hydrogen, helium provides about 8% to 12% less lift than hydrogen, and was not readily available to Germany compared to hydrogen during the Hindenburg's design phases. As Germany sought to be more convenient and effective for larger payloads and a longer range, they decided to use the flammable hydrogen rather than the non-flammable helium. This disaster could have been prevented if Germany valued safety more than profitability and convenience. They could have used helium instead of hydrogen, or even better grounding procedures and static electricity control to prevent such a disaster from ever happening. As a result, the consequences were severe. 36 people lost their lives, and many others were seriously injured. The disaster was captured on film and broadcast around the world, leaving a lasting emotional impact. Economically, one of the largest and most expensive airships ever built was completely destroyed, and the disaster effectively collapsed the airship passenger industry. Although the environmental damage was limited, public trust in airship travel was shattered, marking the end of the airship era and the beginning of airplanes as a means of travel. The Hindenburg disaster led to major changes in aviation design and safety. Most importantly, it marked the end of hydrogen-filled passenger airships, as engineers recognized the extreme risks of using flammable gases for lift. Airships were quickly replaced by airplanes, which were becoming faster, safer, and more reliable. Engineers now understood the importance of prioritizing safety over convenience and profitability, as while hydrogen was better in many aspects compared to helium, flammability made it a dangerous choice compared to helium. Overall, the Hindenburg disaster shows how even one engineering decision can lead to catastrophic consequences. To this day, this case reminds engineers to prioritize safety and consider real-world conditions and scenarios. In the end, failure in engineering is never just technical, it's human.